Section 3.4, we're going to be talking about polynomial functions. Their graphs, applications, and models. Okay, so let's start off talking a little bit more about graphing. Remember, factoring is the most important thing that you'll learn in math. We've talked a lot about factoring. There's some supplemental material on that too. But graphing is the second most important thing. And with graphing, it's important that you understand parent graphs, the main shapes of graphs we've gone over, as well as how to transform them with translations, dilations, and reflections. So in general, a graph will have as many turning points as its degree minus 1. So what that means is if you have x to the second, the degree is 2, right? So here's the turning point right here. X to the third looks like this. All right, so I mean there's one turning point there, but an x to the third graph could also look like this. 1, 2. That's what it could look like. So instead of saying a graph will have, we could say, I think can would maybe be a better word. It can have as many turning points as its degree minus 1. Okay. In general, x to an even power is going to look like a parabola, meaning the ends are pointing in the same direction. In general, x to an odd power, the ends are going to be pointing in different directions. What I wanted to do is maybe make a little table for this. We'll have our leading coefficient as our first column. We'll have its degree as another column. And then as x approaches negative infinity on the left, and then x approaches positive infinity from the right. So let's take a look. Let's say if the degree is even. And the leading coefficient is positive. So let's say we have something like y is equal to, it doesn't matter. Let's say just positive x to an even power. The graph's going to look something like this. Now what this means x negative infinity, we've talked a little bit about that with domain. This just means on the left side of the graph. And as x goes to positive infinity, that just means the right side of the graph. So look at the graph that I just drew. On the left side of the graph's going up. On the right side of the graph, it's going up. The way that we write that, it's similar with range, is we say that y goes to positive infinity. When y is going to positive infinity, that means the graph's going up. What if we had also an even degree, but what if we had a negative leading coefficient? You know at this point that when you multiply by a negative, that reflects the graph over the x-axis. And the left side, the graph is now going down. Negative infinity for y. And on the right side, the graph's also going down. Negative infinity. All right. Let's take a look at odd degrees. we'll start with if the leading coefficient's positive x to an odd power generally looks like a squiggle. On the left side of the graph, it's going down, but on the right side of the graph, it's going up. If the leading coefficient's negative, it's just flipped upside down. So now on the left side, you can see it's clearly going up. And on the right side, the graph is now going down. This is called end behavior. This stuff, these last two columns, that's called end behavior. So if we know what's going on at the ends of the graph, we could kind of figure out what's going on in the middle. And end behavior is just based on the highest power of x. That's going to determine the shape of the graph. Next, let's talk about multiplicity, and then we'll do some more examples. We have already talked a little bit about multiplicity. What multiplicity means is it means how many times is the same number a root, x-intercept, or 0. And it could happen an even number of times. Like you could have the same x-intercept that's occurring twice, like x equals 2 and x equals 2. If it happens an even number of times, then the graph is tangent to the root. Really what that means is it just bounces off the x-axis there. So like if that happens an even number of times, you can see the graph just bounces off. But if you have an odd number multiplicity, then the graph goes through the root. So let's say x equals 2 just once, or let's say x equals 2 5 times. The graph's still going to go through it, and there's no bouncing going on here. That's what multiplicity means. So next, let's figure out end behavior. We'll do some examples with that. We'll describe the end behavior of, I have 4 examples. Let's say f of x is equal to x to the 4th minus x squared plus 5x minus 4. And say g of x is equal to 3x to the 3rd minus x squared plus 2x minus 4. And h of x is equal to negative x to the 6th plus x to the 2nd minus 3x minus 4. And the last one, let's say p of x is equal to negative x to the 7th plus x and then plus 4. When we're talking about end behavior, that just means what's going on at the ends of the graph. And in order to figure that out, we said end behavior, you look at the highest power of x. So I'm going to go through and I'm just going to circle them here. Nothing else matters when we're talking about end behavior. If you go back to our chart, you could figure out what this looks like. But in general, x to an even power looks like this. If you have a negative in front of it, it gets flipped over. X to an odd power looks like this. If the leading coefficient's negative, it gets flipped over. So I'm just going to sketch these graphs. I don't know what all the other stuff means, but generally the ends, this graph's just going to look like this. It's x to an even power. The 3 is going to stretch it, but in general, anything to a third power looks like this. Anytime you have an even graph, x to the 6th is an even power, it's going to look like this, but notice there's a negative in front of it. So the graph's going to look something like this. It might actually even look like this. It might have 5 turns. 1, 2, 3, 4. Let's see here. Did I do an extra one? 1 turn, 2 turns, 3 turns, 4 turns, 5 turns. There we go, like that. So in general, it's going to take the same shape. Still kind of looks like a parabola, but it's going to be upside down. We don't know which one it is, and that's not important right now. Generally, we just know that it's upside down. And then x to the 7th, instead of looking like an odd function, there is a negative in front. So it's going to start upside down like that. Now it might have 6 turns. 1 turn, 2, 3, 4, 5, 6. That's what it could look like. We're not really sure. So let's just look at the ends of these graphs. And we'll make a little table here. As x approaches negative infinity, and as x approaches positive infinity, let's go through and let's talk about what the graph's doing. Okay, so this first graph, it looks like on the left side of the graph, y is going up to infinity, and on the right side of the graph, it's also going up to positive infinity. On the left side of the next graph, graph B, it looks like y is going down to negative infinity, and on the right side, the graph is pointing up to positive infinity. The next graph, negative x to the 6th, looks like on the left side, y is pointing to negative infinity, and on the right side, y is also pointing to negative infinity. And in the last graph, on the left side, the graph's going up, but on the right side, the graph is going down. All right, so now let's graph some actual equations. Graph the following, and we'll also get the x and y intercepts. Okay, so let's start with f of x is equal to 2x to the 3rd plus 5x squared minus x minus 6. Start by getting the y-intercept by making x equal to 0. And f of x is the same thing as y, and if we plug 0 in for all the x's, it's going to cancel these terms out, and we're just left with negative 6. Okay, so now let's get the x-intercepts. And when we're looking for the x-intercepts, can't solve it because it's too basic, or it's not basic. It's not quadratic, so we can't use completing the square or quadratic formula. There's an even number of terms, but I could tell if we take out a GCF, it's not going to factor by grouping. So the only other technique that we know is the rational root theorem. The first technique is we figure out the number of positive roots. So it's going to be positive, positive, negative, negative. It looks like there's going to be one positive root. The number of negative roots. We change the odd powers of x. That's odd. That's odd. I joke with my students in high school and I tell them I'm odd, but this would be negative, positive, positive, negative, changing the odd powers of x, and that comes up with 2 or 0. As far as what they could be, we'll list our p over q values. P, remember, are factors of 6. Q, remembers, are factors of 2. Factors of 6 are 1, 2, 3, and 6. Factors of 2 are 1 and 2. So when we go to list what the rational factors could be, it's going to be 1 over 1 and 1 over 2. 2 over 1 and 2 over 2 we already have. 3 over 1 and 3 over 2. And then 6 over 1 and 6 over 2 we already have. Step 4, let's find the roots. We're going to use a combination of the remainder theorem and synthetic division. So I'm going to get my calculator ready to go. And let's see, we'll start with 1. If x is equal to 1, I'm going to store that, and let's see what the remainder is. 1 store a, and then I'm going to type 2 mem variable a to the third plus 5 mem variable a squared minus mem variable a, and then minus 6. So if 1's stored in, we get a remainder of 0, which is nice. So we know 1 is definitely one of the roots. And let's find the other 2. I'm going to do synthetic division on 1 and 2x to the third plus 5x squared minus 1x minus 6. So we get 2, 2, 7, 7, 6, 6, remainder nothing. Our pressed polynomial is 2x squared plus 7x plus 6. Let's factor that trinomial. So factors of not just 6, remember it's always AC, right? So 2 times 6 is 12, that add up to 7, 4 and 3. So this would factor to be 2x squared plus 4x plus 3x plus 6 equals 0. Cutting it down the middle, we could take out a 2x. We're left with x plus 2. Take out a 3, we're left with x plus 2. So we get x plus 2 times 2x plus 3. And we get x is equal to negative 2, and x is equal to negative 3 halves. Negative 2 is right here. Negative 3 halves is negative 1.5. That's like right here. And looking at the end behavior, 2x to the third is a cubic. It's positive, so it's going to take that general shape. So we're going to go up. I don't know how far up to go, so you'll learn that in calculus, but in this class we have that general shape. You should be able to do that. We'll do one more problem like this. What if I asked you to graph and get the x and y intercepts for f of x is equal to negative x minus 1 times x minus 3 times x plus 2 to the second. Now, how many roots are there? How many total? Well, it's a little tricky to see here, but let's write it all the way out. X minus 1 times x minus 3 times x plus 2 times x plus 2. Looks like there's 4 total roots. We have 1, 2, 3, and 4. Negative 2 looks like it has an even multiplicity. Negative 2 has a multiplicity of 2, meaning it happens twice. So when we go to graph this, we're going to have to bounce off negative 2. And then we have other roots at 1 and 3. Those are our x-intercepts. Now let's find the y-intercept by putting 0 in for all the x's. And we get y is equal to negative 0 minus 1 times 0 minus 3 times 2 to the second. The y-intercept would be 1 times negative 3 is negative 3. Negative 3 times 4 is negative 12. And looking at the end behavior of the graph, well, if we were to multiply all these out, we would have the leading coefficient would be x times x times x times x, or x to the fourth with a negative in front, right? So the leading term, if we were to distribute everything, the leading term would be negative x to the fourth, which would be like a parabola but upside down. So let's go ahead and connect our dots. Let's see here. And remember, it bounces off -2, right? That's what it would look like. We're going to finish with talking about how to find all possible roots, even if they're not irrational. That's called the location principle. If there's no rational roots or rational zeros, what we do is we use what's called the location principle. And upper, lower bounds. I'll walk you through one. Okay, let's take a look. Say if we had a problem like this. Say f of x was equal to 2x squared minus 7x plus 4. Now we could graph this using the quadratic formula, but I want to show you how this location principle works. Similar to rational root theorem, let's find the number of positive roots. And the positive roots would be positive, negative, positive. There's two changes here, so there would be 2 or 0 positive roots. Next step is we find the number of negative roots. Change the odd powers of x. Positive, positive, positive. There's no negative roots. What we're going to do next is a little bit different. This is what the location principle looks like, and it's like synthetic division, but we're going to do it a little bit more efficiently. If we have irrational roots, you can't tell me the root is like the square root of 2. You can't just find that on your own. It's going to be somewhere between 1 and 2. That's what we're looking for. Like if one of the x-intercepts is pi, 3.14, because it's irrational, you can't tell me the exact number. The closest you could do is tell me between what two numbers it is. So let me show you how to do this. I'll show you how to find it first for the positive roots. And because this is sort of like synthetic division, we're going to start off with 2, -7, and 4. The way location principle works is you always start at 0 and then go up by 1 each time. So I'll do it off on the side and you can see how it translates over to this. We're going to do synthetic division with 0 first. First thing we do is bring down the 2. 2 times 0 is 0. Bring down, add them up, you get -7. Multiply by 0 and you get 4. So it's going to be 2, -7, and 4. Now with the location principle, this step is in our head. It helps us save a little bit of work and it helps us do this a little bit quicker. Let's try the 1. We're going to do synthetic division with 2, -7, and 4. Bring down the 2. This would be 2, -5. This would be -5, and this would be -1. So the way that we would do this, we don't actually have to write the synthetic division part. I'm just showing you how it works. We're doing this part in our head. What I would do is I would start here and bring the 2 down. 2. 2 times 1 is 2. If it helps you, maybe write a little 2 here and then add those together. You get -5. Then -5 times 1 is -5. Maybe write it over here. Add those together. You get -1. All right, so hopefully that makes some sense. Let's try with the 2. I'm going to bring the 2 down. 2 times 2 is 4. I'm going to add that with -7, and you get -3. -3 times 2 is -6. I'm going to add that with 4, and I get -2. What I'm actually looking for here is for all of these numbers to be the same sign. That's going to be what's called an upper bound. Let's bring the 2 down. 2 times 3 is 6, so this would be -1. -3 would be 1 here. And then we'll try the 4. 2 times 4 is 8. 8 plus -7 is 1. 1 times 4 is 4. Plus 4 is 8. So what we have here is we have what's called an upper bound. An upper bound means when you're looking for your irrational roots, it's hard to know where to stop. But the upper bound is where all the terms are the same sign. Now remember, 0 doesn't count. So if you were to get 0 here, like if it were 2, 0, and 8, you would have to keep going. You want all positive terms. 0 is not positive or negative. So the upper bound in this case is 4, which means that there's no more roots past 4. You don't have to check anymore. You go up until you hit an upper bound. Now where are the roots? If the roots are irrational, you look at the last numbers. You see how 4 and -1 change signs? And you see how -2 and 1, they change signs? There is a root where the remainders change sign. The remainder is the last number. So 4 occurs when x is 0, right? 1 occurs when x is 1. So we say that there's a root between when x is 0 and when x is 1. There's also a root between when x is 2 and x is 3. So what this looks like if we were going to graph this, somewhere between 0 and 1, there's a root. I don't know where it is, but somewhere between there. And somewhere between 2 and 3, there's a root. Okay, so those are the positive x-intercepts. Let's do the negative now. When x is negative, what we're going to do is we are going to change the signs of the odd powers of x. And we're going to do exactly the same process. So remember how it was 2x squared? So we're going to write 2x squared, but instead of being -7x, we're going to put +7. And then our number is 4. And we're going to do the same thing. We're going to do 0, 1, 2, 3, 4. We might have to go more. We're looking to see where do the signs stop changing. Bring the 2 down, 2 times 0 is 0, 7 down, 7 times 0 is 0. And look at that. You see how all of these numbers are the same? All of these numbers are the same I'm talking about? That's called a lower bound. The lower bound happens with the negative numbers. The lower bound happens where all terms are the same sign. So it's just like upper. The difference with upper bounds is that happens with the positive x-intercepts. Lower bounds happens with the negative ones. There's a lower bound when x is equal to 0. Looking at this equation, to get the y-intercept, we put in 0 for all the x's. And we get the y-intercept as 4. So if we were just going to roughly sketch this graph, it would go through the y-intercept and like something like that. That's how we use the location principle. So I wanted to maybe do a couple more, just so you get the idea, and then that'll be it for this section. And by the way, we don't have to do all these other numbers here. We already hit a lower bound when x is 0. And just square that off too. Okay, so let's try another example. 2 more actually. How about if we had f of x is equal to 2x to the 4th minus 5x to the 3rd plus 3x plus 1. First step, how many positive roots? Positive, negative, positive, positive. There's going to be 2 or 0. How many negative roots? Well, we're going to change the odd powers. So this would be positive, positive, negative, positive. So there's 2 or 0. Let's find them. We'll go after the positive roots first. And the way that this works is this is after the rational root theorem. So remember our chart. We try to solve to get the x-intercepts. If it's basic, like a linear, that works. We could also factor. We could complete the square. We could use quadratic formula. We talked about the rational root theorem. And this is called location principle. So this is like the most extreme. One other technique that we did learn about is called quadratic techniques. But that only happens if you have like a rational exponent or like radicals, or we did do some examples like that in a previous section. So let's go ahead and find these. Remember, we are doing division, so we want to make sure we have all the different powers represented. We'll start at 0, and I don't know when we're going to have to stop, but we'll stop once all of the numbers are the same sign. So 0 is always going to be the same first row, because you're just adding 0 to those. But now let's be careful going forward here. Bring the 2 down. 2 times 1 is 2, plus negative 5. Negative 3 times 1 is negative 3. This would be 0 and 1. No bound. There's no change at the end for the remainder, so we'll keep going to 2. 2 times 2 is 4, and negative 5 is negative 1, negative 2, negative 4, and negative 2. So this means that there is a root between, I abbreviate between b/w, x equals 1, and x equals 2. Let's go to 3, bring the 2 down, that's 6, so this would be 1, 3 would be 3, 9 and 3 is 12, 12 and 3 is 36, plus 1 is 37. There's another root between x equals 2 and x equals 3. So we don't have to try 4 and 5, we actually hit a upper bound right here. The upper bound is equal to 3. And we have our roots, so now let's find the negative ones. Remember, we are going to change the signs of the odd powers of x. So we have x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, and our number. 2x to the 4th, but instead of negative 5, we're going to put positive 5. No x squared. Instead of 3x, we're going to put negative 3, and then 1. So start at 0. Nothing going on there, so we'll go to 1. So let's see, this would be 2. 2 times 1 is 2, so 7 and 1 is 7. 7 and 1 is 7, plus negative 3. 4 is 4, plus 1 is 5. So actually we hit another bound here. Our lower bound, just be careful. Remember, these are negative x values. So the lower bound isn't 1, and because it's being worked on in the negative x's, the lower bound would actually be negative 1. And looking at the end, there's no changes. So that means that there's no negative x-intercepts. And that's fine, because we said we could get 2 or 0 negative, right? And we got no negative. So what does this graph look like? Well, there's a root between 1 and 2, between 2 and 3. The problem has a y-intercept of 1. So if we're going to graph this, it looks something like this. Something like that. That's all we really know. Let's try one more. This will be our last problem in this section. What if it was f of x is equal to 4x to the 3rd plus 4x squared minus 5x minus 3? First step, how many positive roots could we expect? Positive, positive, negative, negative. Looks like there's 1. Negative roots. We're going to change the signs of the odd powers of x. Negative, positive, positive, negative gives us 2 or 0. And now let's figure out where they are. Four, 4, -5, and -3. All the powers are represented. We'll start at 0, and we'll see when we have to stop by hitting an upper bound. At 0, we're adding 0 to all of these. Let's go to 1. Bring the 4 down. 4 times 1 is 4, plus 4 is 8. 8 times 1 is 8, plus -5 is -3. I think 8 plus yep. Wait a minute. 8 times 1 is 8, plus -5 is 3. 3 times 1 is 3, plus -3 is 0. What does that mean when the remainder is 0? That the root is at x equals 1. We did talk about that. Remember, that was the factor theorem. We talked about that when we were talking about the remainder theorem. So, but 0 doesn't have a positive or a negative sign, so let's keep going here. Let's try 2. Bring the 4 down. It's 8 plus 4 is 12. 24 minus 5 is 19. 19 times 2 is 38. So this is 35. All right, well, that's a big stop sign. We hit an upper bound when x is equal to 2. And we only found one root, which is exactly what we were expecting. Let's find the negative roots. We'll change the odd powers of x. So we have 4x to the third, so I'm going to make that -4. 4x squared, positive 5x, and then -3. I'm expecting 2 or 0 changes, so let's see what happens. -4 times 1 is -4, so this is 0, 5. 5 times 1 is 5, plus -3 is 2. So this means that there's a root between x equals 0 and x equals -1. Remember, these are negative roots, right? So don't just write 1, that's wrong. Let's try -2. -4 times 2 is -8, plus 4 is -4. -8 plus 5 is -3. -3 times 2 is -6. -6 plus -3 is -9. So we have another root between when x is -1 and when x is -2. So we do have 2 negative roots, and we also hit a lower bound when x is equal to -2. All right, so let's graph this. We have 3 roots. It's 4x to the third, so that all makes sense. We have a root at 1, between 0 and -1, somewhere in between, and between -1 and -2. Now the y-intercept is -3. Because if you plug in 0 for all the x's, you would get y is equal to -3. The end behavior is based on 4x to the third, so the graph looks something like this. So let's connect the dots. And that's how you graph a polynomial.